In this video, we're going to learn about innumeracy and natural frequency. Numeracy is the ability to reason and to apply simple numerical concepts. Innumeracy is an inability to deal comfortably with the fundamental notions of number and chance. Innumeracy plagues far too many knowledgeable citizens. And confoundingly, it's often flaunted by statements like, "I can't even balance my checkbook. I'm a people person, not a numbers person." How comfortable would you be estimating the following? How fast does human hair grow in miles per hour? How many people die on Earth each day? How many cigarettes are smoked annually in the United States? Innumerate people have difficulty approaching problems like these. Some common inadequacies result from innumeracy. Chief among them is a lack of numerical perspective. Many people just don't know how to process numerical information for making decisions. A lack of numeracy leads to exaggerated appreciation for meaningless coincidence. If you've ever received a phone call from someone you were just thinking about and imbued that with cosmic significance, then you know exactly what this means. Innumeracy can lead to people accepting statements of pseudosciences as credible. It also makes it difficult for people to recognize social trade-offs. Here's one potential consequence of innumeracy. The gap between scientists' assessment of risks and the popular perceptions of those risks threatens to eventually lead to either unfounded and crippling anxieties or to impossible and economically paralyzing demands for risk-free guarantees. Innumeracy and pseudoscience are often connected because of the ease with which mathematical certainty can be invoked to bludgeon the innumerate into acquiescence. Scientists reveal 36 inches equals 1 yard underwater, a perfectly meaningless statement that sounds absolutely certain. Pseudosciences include things like parapsychology, predictive dreams, astrology, medical fraud, and numerology. Those who lack numeracy are more prone to believe in these pseudosciences. Practical difficulties arise when the innumerate are dealing with large numbers. We lack an intuitive feel for these numbers. When people hear the U.S. debt in 2019 was $22 trillion, they have no way to process that, and they tend to focus on the 22, which itself is not such a big number. But consider, if you spend $1 a second, how long would it take you to spend $1,000? The answer is 17 minutes. How long would it take you to spend $1 million? That's about 12 days. Then how long would it take you to spend $1 billion at $1 a second? That would take 32 years. And to spend $1 trillion at $1 a second would take 31,710 years. Very small numbers like 1 in 10,000, 1 in a million, 1 in a billion, quite common when dealing with probabilities, also present challenges to the innumerate. How do we process ideas like 1 chance in a billion? That's like 1 penny in $10 million, or 1 second in 32 years. Even then, the innumerate might be inclined to say, yes, but what if you are that one? There's a tendency to personalize on the part of the innumerate, and this leads to number confusion. The inability to understand statistical information is not a mental deficiency. It's largely due to the poor presentation of the information. Poorly presented statistical information can cause erroneous communication of risks with serious consequences. Single event probabilities, conditional probabilities such as sensitivities and specificities of tests, and relative risks are confusing because they make it difficult to understand what class of events a probability or percentage refers to. Reference classes are important. There's a 60% chance of rain tomorrow is a probability statement about a single event. It will either rain or not rain tomorrow. Single event probabilities are a potential source of miscommunication because they leave open the class of events to which the probability refers, or the reference class. Some people think it will rain tomorrow in 30% of the area. Others think that it will rain 30% of the time. And a third group thinks that it will rain on 30% of the days like tomorrow. Area, time, and days are examples of reference classes, and each class gives the probability of rain a different meaning. Here's a reference class example. A doctor prescribes a drug to patients and says they have a 30 to 50% chance of developing a sexual problem, such as impotence or loss of sexual interest. Patients understood this to mean that they would have problems in 30 to 50% of their sexual encounters. The doctor was thinking in terms of patients, but the patients were thinking in terms of their own sexual encounters. Frequency statements always specify a reference class. Thus, misunderstanding can be reduced by two mind tools: specifying a reference class before giving a single event probability, or only using frequency statements. So this could be restated: of all the people who take this drug, 30 to 50% will develop a sexual problem. For each confusing representation of numbers, there's at least one alternative, such as natural frequency statements, which always specify a reference class and therefore avoid confusion, thereby fostering insight. Simple representations of risk can help professionals and their constituents move from innumeracy to insight and make consultations more time efficient. The takeaway point is we need to know how to represent information so that users of that information, decision makers, patients, and others, can actually understand what it means. The chance of a test detecting a disease is typically communicated in the form of a conditional probability, the sensitivity of the test. If a woman has breast cancer, the probability that she will have a positive result on mammography is 90%. This statement is often confused with the following: if a woman has a positive result on mammography, the probability that she has breast cancer is 90%. That is, the conditional probability of A given B is confused with that of B given A, and the results can be stressful or sometimes far worse. Assume you use mammography to screen for breast cancer. The following information is known. The probability that a woman has breast cancer is 1%. This is the prevalence of breast cancer. If a woman has breast cancer, the probability that she tests positive is 90%. This is the sensitivity of the test. If a woman does not have breast cancer, the probability that she nevertheless tests positive is 9%. This is the false positive rate. A woman tests positive. What's the chance she actually has breast cancer? When 160 gynecologists were asked this question, a 60% majority believed that the answer was 80 to 90%, and 19% believed it to be a 1% chance. If patients knew about this variability, error in interpretation among doctors, they would be rightly scared. Natural frequencies, in contrast, help us to see through this mental fog. To express them, you take a large enough number of people, such as 100 or 1,000, depending on the prevalence of the disease in this case, and you break this number down into natural frequencies. 10 in every 1,000 women have breast cancer. Of these 10 women with breast cancer, 9 will test positive. Of the 990 women without breast cancer, about 89 nevertheless will test positive. Now it's easier to recognize the answer. We expect that 98 women test positive altogether, 9 of whom have breast cancer. Therefore, the positive predictive value is 9 out of 98, or 9.2%. Roughly 1 in 10 is the probability that a woman who tests positive for breast cancer actually has breast cancer. So we expect that of 10 women who test positive, 9 have false positive results. Here is one way to present this information. Notice that the desired answer is not readily apparent. It requires an application of Bayes' theorem shown at the bottom of the slide. Here is the same information presented somewhat differently as a result of a Bayesian flip of the initial probability tree. Most people, especially decision makers and patients, are not particularly familiar with Bayes' theorem or Bayesian flips. Here is the same data presented as a natural frequency. Notice it begins with 1,000 women, and it splits that into 10 of 1,000 women have breast cancer, and 990 of the 1,000 women do not have breast cancer. Of those who have breast cancer, of those 10 women, 9 will test positive for breast cancer, and 1 will not. Of the 990 women who do not have breast cancer, 89 will still test positive for breast cancer. 901 will not. So when we look at all of those who test positive for breast cancer, we see 9 women who actually have breast cancer and 89 who do not. 9 divided by 98, the sum of these two, is 0.092. This is far more intuitive than Bayes' theorem or Bayesian flip. If you must present probability information in a decision meeting, consider using natural frequencies.